Hello everyone from Math 2000. It's discrete mathematics. It's Professor Wenson here again with a video on your Zybooks section 13.5 titled Graph Connectivity. And let's just get into it. More graph theory stuff. Alright, so the first part of this section is on connected components of a graph. Alright, so there are a lot of definitions in this section as well. You've noticed almost every section here. This whole chapter 13 is comprised of a lot of definitions because the whole chapter is basically just an introduction to graph theory. Alright, so in an undirected graph, if there is a path, remember a path meant an open trail where there were no repeated edges and no repeated vertices. Or it was an open walk, right? A trail with no repeated vertices. So if there is a path from vertex V to vertex W, well then there's also a path, the other way around. You just go back. So then they say that the two vertices, V and W, are connected if there's a path between them. A vertex is always considered to be connected to itself. Alright. If the graph represents a road or communication network, then it is very desirable for every pair of vertices to be connected. Alright, so if you think of roads, and maybe all the vertices are towns, if every pair of vertices is connected, means there is a path from between every pair of towns. There's a way to get from every town to every other town. The property of being connected can be extended to sets of vertices and an entire graph. Alright, so, and more definitions here. A set of vertices in a graph is said to be connected if every pair of vertices is connected. Alright, so you pick any two vertices in the vertex set, or in whatever set of vertices you're looking at. Right? If every pair of vertices has a path between them, then the set of vertices is called a connected set. Right? And then the entire graph, right? A graph is said to be connected if every pair of vertices in the graph is connected. All right. And it's called disconnected otherwise. So that means if you can find a single pair of vertices that aren't connected, well then the graph's called disconnected. Pardon me. But a disconnected graph can be broken up or divided into more than one connected component, right? The title of this part of the section. So the animation below illustrates the idea of connected components. So here's a graph here, and I'll start playing this animation for you. So there's a graph with vertices A through H, looks like. No, A through I. And you see that, vertex D and vertex I are connected, right, because there's a path between them. I mean, same thing for D and H and I. Basically, every vertex in this part of the graph, A, I, H, D, and F, is connected, right? So this would be an example of a connected component. Whereas, E, C, and G form another connected component. And vertex B is also, connected. Remember, every vertex, they said, is connected to itself. So vertex B all by its lonesome here is also a third connected component of this graph. Well, let's continue. A and E aren't connected because there's no path that can take me from vertex A to vertex E. So this graph would be considered a disconnected graph, again, but with 3 connected components. Right. And like I said, vertex B is what they call an isolated vertex. Right? It's not connected to any other vertex. So yeah, so the connected components are what they've circled here, as I've pointed out with my talk earlier. And then you see if you remove, see, it says you know, the set of vertices A, D, F, and H is not a connected component because it is not maximal. Right. I think they mention it down here because, you know, if you add vertex I, it makes the piece even bigger. Right. So pieces of a connected component aren't themselves connected components. All right, so they get a more formal definition of connected component here. A connected component of a graph. It is a maximal set of vertices that is connected. The word maximal means that if any vertex is added to a connected component, then the set of vertices will no longer be connected. So like back up here, you know, A, D, F, H, and I form a maximal set of connected vertices. Therefore, this is a connected component. And it's a maximal set because if I added any other vertex, say vertex C, to this set here, then you're disconnected. All right. Adding any one of these other 4 vertices to this set would give me a set of disconnected vertices. So this is a maximal set. Same thing for these 3. E, C, and G. This is a maximal set of connected vertices, right? Because if I added any other vertex to this set, we'd have a disconnected set. Right. And as mentioned, a vertex that is not connected with any other vertex is called an isolated vertex, right? And is, you know, a connected component with only one vertex. Pardon me. All right, so look at this example here. Just answer some simple questions to start. You know, is vertex 8 connected to vertex 9? Well, yes. There's a path from 8 to 4 to 9. So there's a path from 8 to 9. Yes, they're connected. Is vertex 8 connected to vertex 3? No. There's no path connecting vertex 8 and vertex 3. Is the set of vertices 4, 6, 7, and 8 a connected component of the graph? Let's see, 4, 6, 7, and 8. Well, no. Because, I mean, yes, they are connected. Right? They're all connected. But if I put vertex 9 in there, you know, that is also connected. There's an even larger set. So the 4, 6, 7, and 8 is not a maximal set of connected vertices. I can throw in vertex 9 and make an even bigger set of connected vertices. So just 4, 6, 7, and 8, that piece of the graph is not considered a connected component. How about the set with just vertex 1? Well, yeah, this is one of those isolated vertices, and it's connected to itself. And if I added any other vertex, you'd be disconnected. You'd have a disconnected set. So this is indeed, any isolated vertex is a connected component of a graph. Is this graph connected? Well, no. Remember, in order for a graph, the whole graph, to be considered connected, every pair of vertices must be connected. Well, we already saw 8 and 3 are not connected. There's, you know, 3 separate components here. So definitely not a connected graph. Okay, so again, hopefully some simple definitions. All right, so now more definitions. All right, now this one's maybe a little trickier. We'll see. So the concept of K connectivity. So in some networks, it is important to be able to guarantee connectivity, right? Even if one or more vertices or edges are removed from a graph. For example, in a communications network, switches, which would correspond to vertices in the graph, can fail. But you want to have it set up so that even if some switches fail, everyone can still call everyone else, right? There's still a connected path between each pair of vertices. Same thing for a road network. It would be desirable that even if, like in a road network, right, a road could become unavailable due to an emergency or heavy traffic. But even so, right, even if if you removed an edge, if a road was shut down, or several roads were shut down, you'd still would like to have the network be connected. You'd still like to be able to get between any pair of towns. Again, the towns are the vertices here, even if some roads were, shut down for some reason. So the definition of connectivity can be extended to encompass resilience to vertex or edge failures. Right? So this is kind of a talk of how well connected are the points on my graph, right? Are the vertices. And it's based on how many vertices could I remove and have the graph still be connected? Or how many edges could I remove and have the graph still be connected? And this is called connectivity. All right, so there's, again, two definitions here. One about being k vertex connected, and one about being k edge connected. So an undirected graph G is k vertex connected if the graph contains at least k plus 1 vertices, right? You can't talk about k vertex connected unless you have more than k vertices. If the graph contains at least k plus 1 vertices and remains connected after any k minus 1 vertices are removed from the graph. So for instance, you could say any connected graph is one vertex connected because if you remove any 0 vertices, if you remove nothing from the graph, it'll still be connected. But we're going to try to find the largest value possible for k for any particular graph. And or another example, right? If a graph were 3 vertex connected, that means you could remove any 2 vertices, right, k minus 1, and it would still be connected. All right, so the vertex connectivity of a graph is the largest value of k, such that the graph is k vertex connected. And this vertex connectivity of a graph G is denoted by k of G here, or kappa of G, Greek letter, it's a little k, but Greek letter kappa. All right. And the vertex connectivity of a graph is the minimum number of vertices whose removal disconnects the graph into more than one connected component. All right. So if I say the vertex connectivity of a graph is 5, that means removing there is a set of 5 vertices I could remove to make the graph disconnected. Right. And if it's 5 vertex connected, that means I could remove any 4 and it would still be connected, any 4. But then when I get to there is a set of 5 I could remove, and then it would be disconnected. We'll see some pictures and examples in a minute. And then the same concepts for edge connected. Right? This, instead of removing vertices, you talk about removing edges. So here an undirected graph G is k edge connected if it remains connected after any k minus 1 edges are removed from the graph. So again, for example, if a graph were 3 edge connected, that means I could remove any pair of edges, any 2 edges from the graph, and it would still be a connected graph, not broken up into components. Now the edge connect, we're going to try to find the largest value of k for which this happens, and that's called, the edge connectivity of the graph. The edge connectivity of a graph is the largest value of k such that the graph is k edge connected. And if that's the case, and it's denoted by this lambda of g, that's the edge connectivity of a graph G. And so, in other words, the edge connectivity of a graph is the minimum number of edges whose removal disconnects the graph into more than one connected component, breaks it up. So again, for instance, if a graph had an edge connectivity of, say, 5, then that means it's 5 edge connected. So I could remove any 4 edges and it would still be connected. But there is a set of 5 edges I could remove and disconnect the graph. Pardon me, a little scratch in my throat. Alright, so let me show you this animation here. Alright, this is a graph with, there are, 9 vertices and a bunch of edges. Let me play this animation for you. Alright, so first they're talking about vertex connectivity. You see that removing these 2 vertices, and when you remove a vertex, all the edges are gone because there's no vertex to build a road. It's like there's no city to build a road to, so why have the roads? If I remove, these 2 vertices, you see how they like erase them in yellow here. Well, if I remove these 2 vertices, the graph is broken up now. Instead of being connected, now it's broken up into these 2 components. So if I remove 2 vertices and the graph is now disconnected, we would then say the graph is not 3 vertex connected. Because if it were 3 vertex connected, that means I could remove any two vertices and it would still be connected, but we see that's not happening here. So the most connected, vertex connected this could possibly be would be 2 vertex connected. Right? If you're not 3 vertex connected, you're not going to be 4 vertex or 5, you're not going to be any higher vertex connected. So if we're not 3 vertex connected, the highest you could possibly be is 2 vertex connected. And they say, see here, removing any single vertex, right? Take out any of them. If you were to remove any single vertex, it would still be a connected graph, even with that vertex gone. So if you can remove any single vertex and it's still a connected graph, then you're called 2 vertex connected, right? Again, this is the maximal number for which we have, connectivity. So they'd say the vertex connectivity of the graph is 2. Right? And that would be that kappa of G. And another way of thinking about the vertex connectivity being 2, right? That means it's 2 vertex connected. So I could remove any vertex, any single vertex, 1 vertex, and it's still connected. But then there is a pair of vertices out there that I can remove to disconnect, as they showed in the first part of the animation. Alright, then they talk about edge connectivity. Look at these 3 edges here. If I remove those, it's broken up into 2 pieces, right? The isolated vertex now, getting rid of these, and then you have this big piece here. But you see how removing 3, there are some 3 edges I can remove to disconnect the graph. So we would say that this graph is not 4 edge connected, right? Because again, if it were 4 edge connected, I could remove any 3 edges and it would still be connected, but we're saying that that's not happening here. I have found an example of, or they have found an example of 3 edges you can remove to disconnect the graph. So it's not 4 edge connected. So that means the highest edge connectivity could be is 3. It could be 3 edge connected or 2 or 1. So let's play this more. And it says here, after removing any 2 edges of the graph, it is still connected. So you see they go around here. Now, they don't show you all of them, but if you removed any pair of edges, take out any 2 of these, the graph will still be one connected component. It'll still be a connected graph. So if you remove any pair of edges and it's still connected, then they call it, 3 edge connected. And if that's the largest value of edge connectivity we can see, then that's called the edge connectivity of the graph. Right? So they're saying the edge connectivity of this graph is 3. Right? So you see the vertex connectivity is 2, the edge connectivity was 3. So that just please be aware that vertex connectivity and edge connectivity are not going to necessarily be the same number. Alright, so hopefully that animation helped shed a light on some of the definitions. We'll get to some more examples. Now, this next part kind of gives you a way to cut down the amount of work you need to do to check for vertex connectivity and edge connectivity. Showing that a graph is k-edge connected involves showing that removing any subset of k-1 edges leaves the graph connected. So if a graph has m edges, there would be m choose k-1 subsets you'd need to check. And that can be a lot, especially if there's a lot of edges. Right? So doing all that searching would be infeasible. It would be unreasonable to do that much, especially for all values of k, up to m-1. Fortunately, there are more efficient ways to determine the edge connectivity and vertex connectivity of a graph. The theorem below shows that the minimum degree of any vertex, which is easy to compute, is an upper bound for both the edge and vertex connectivity. Now, it doesn't tell you about what it's going to be equal to, but it does tell you that this is the highest you need to check and then go down. So if you're given an undirected graph and say the minimum degree of any vertex is this delta of g, then the vertex connectivity will be less than or equal to that minimum degree of any vertex, and the edge connectivity will be less than or equal to that minimum degree. Right? So you can start at that minimum degree and see if your graph is that vertex connective or that edge connected. So for example, look back at this picture up here. All these vertices, let's see, this has degree 3, degree 3, degree 4, degree 3, degree 5, degree 6, degree 4, 3, 4, 3. The minimal degree of any vertex, the smallest degree any vertex has is 3. So the edge connectivity and the vertex connectivity will be either 3 or smaller. Which you saw, the edge connectivity was 3 and the vertex connectivity was 2. Right? So that's what this is saying. And they give a really nice, pretty straightforward proof. Here, I'll let you read that. I'm not going to get into the proof. But yeah, so if you know the smallest degree of any vertex, that's the number you're going to start at, right? And then check to see if your graph is that vertex connected or that number edge connected. And if it's not, then you just bump it down 1, check that again. And keep going until you get down to 1. Alright, so here's an example. Define G to be the following graph. Now, the first question is G 3 vertex connected? Is G 3 vertex connected? Now remember what it means to be 3 vertex connected. That means I can remove any 2 vertices, any 2, and it should still be connected. Now if you can find a pair of vertices that, when you remove them, it disconnects the graph, well, then it's not 3 vertex connected. Alright, so hopefully you can see that the answer is no. Because there I can find a pair, I can find 2 vertices here that if you remove them, you'll disconnect the graph. You'll break it up into multiple connected components. And that would be vertex 5 and 6. Can you see? You got to kind of visualize this, and maybe you could draw it. If I remove vertex 5, that gets rid of this 5-7 edge, the 5-2 edge, the 5-4 edge. It gets rid of all that stuff. If I remove vertex 6, it gets rid of the 6-8 edge, the 6-9 edge, the 6-3 edge. And can you see it? Can you picture it? If I remove vertex 5 and vertex 6, there's going to be a big gap between these two like square looking shapes. It'll break the graph up, it'll disconnect the graph. So is the graph 3 vertex connected? No. Because, I can find a pair of vertices that once I remove them, the graph is disconnected. All right, so the answer is no for this first one. Is the graph 3 edge connected? So again, to be 3 edge connected means you can remove any 2 edges and the graph will still be connected. And to say a graph is not 3 edge connected means that there is a pair. You can find one pair of edges that if you remove them, it'll disconnect the graph. And I can see 2 right here. Can you see if I got rid of the edge 3 and 6, the edge between 3 and 6, if I got rid of that edge and also got rid of the edge between 5 and 7, there'd be no connection between these pieces. They'd be disconnected. So is the graph 3 edge connected? No, it is not, because I can find a pair of edges to remove that will disconnect this graph. See, and they're 5-7 and 3-6. If you remove those edges, you'd have this like box here with a little triangle shape popping out. You'd have this box here with the triangle shape popping out, but they wouldn't connect. They'd be 2 separate connected components. All right, now here this is about a totally different graph. So I'll draw this. Right? Remember K5? We talked about, now this is back I think in section 13.1. This K5 was a complete graph on 5 vertices. I'll draw a picture to remind you. Okay. This was a complete graph on 5 vertices, right? You have 5 vertices, and K5 was also called 4 regular. Right? Every vertex has degree 4. Right? So that minimum degree, right, that delta of K5 here was 4, right? This is again this is the minimum degree of any vertex on the graph. Well, they all have degree 4. And by that theorem that was shown you earlier, the vertex connectivity then which was called, that kappa. So the vertex connectivity of, I know my kappa and my capital K look pretty similar. The vertex connectivity will be less than or equal to 4 then. Right, so it could be 4 or less, right, down to 1. Same thing for that edge connectivity. Right, the edge connectivity of this graph, which is was denoted by that lambda, right? Lambda of this complete graph on 5 vertices, again, will be less than or equal to 4, right? This minimum degree of any vertex on the graph. All right, so we start at 4. It is the vertex connectivity 4. Is this graph 4 vertex connected? So if you were to remove any 3 of them, all right, so if I were to take away these 3 vertices, right, I mean, basically that would get rid of all this stuff. And you'd have a connected component. If I were to remove these 3 vertices, I'd get rid of all this pretty much. You'd have this one connected component. And if I were to move this, this, and this, that would get rid of a lot of stuff, but you just have basically the 2 and the 4 line, one connected component. So I mean, yeah, and you can go around. Now there are 5 choose 3 vertices here. That'd be 10 different combinations, 10 different sets of vertices I'd have to look at. But due to the fact that every time I remove 3 vertices, there's just an edge left between the 2 that remain, right? That one component. So this is 4 vertex connected. This is 4 vertex connected. I can remove any 3 of these and be left over with a connected graph. It's still a connected graph. So the vertex connectivity, this kappa of, I'll say of K5, is 4. All right, now for the edge connectivity. All right, now the edge connectivity. There are 10 edges in this. All right, there are 10 edges in this. 5 choose 2, basically, because an edge between any 2. Every pair of vertices has an edge, and there are 5 of them. 5 choose 2. So now the question is, for the edge connectivity, again, I'll start at 4. The edge connectivity could be 4 or less. So I'll start at 4. Is it 4 edge connected? Well, if it were, remember, to check for 4 edge connected, I start removing 3 edges. So if I were to remove, say, I'll just do one example here. If I were to get rid of this edge and this edge, and this edge, you see you still have this like crown shape. It's still a connected graph. And due to the fact that every vertex is adjacent to every other vertex, it's a complete graph, you can remove any 3 of these edges and there's still you can still find a path from one edge to from one vertex to any other vertex. All right, and again, that's due to the fact that every vertex is adjacent to every other vertex. So this, you could do this for any 3. So this is definitely 4 edge connected. It's 4 edge connected, meaning that the the edge connectivity, this lambda, is 4. Okay. Now, I mean, I kind of reasoned that out loud. I didn't really actually go through and check all the possibilities, right? Because again, there are 10 edges, and you're seeing if you remove any 3 of them, that'd be 10 choose 3 possibilities you'd have to go through. So I mean, that'd be 120 different combos that you'd have to act. If you were to actually do every single combo, that's 120. 10 choose 3. Yeah, because that'd be 10 times 9 times 8, and then divided by 3 factorial. Yeah, divided by 6. This, yeah, 720 divided by 6, 120. It'd be 120 different things you'd have to check. I'm just kind of reasoning it out based on the fact that it's complete. Every vertex is connected to every other vertex. It is adjacent to every other vertex. So even if I take away 3 edges, any 3 edges, there's still going to be a path between any pair of vertices. All right. So hopefully that made sense what I said there. All right, so it's 4. The edge connectivity of K5 would be 4. And same thing for the vertex connectivity, as I said, right? 4 as well. Now, as you saw before, this isn't always going to happen, right? You saw in the first example, the first animation, the edge connectivity and the vertex connectivity aren't always the same number. But they are always at most that minimal degree of any vertex. So you can start there. What's the smallest degree of any vertex? And then work your way down. And then now this one, remember this graph, the C10? I'll draw this one up as well. This is one of those cyclical graphs, cycles, 10 cycles. Every single vertex had a degree of 2. Just made kind of a big ring. And again, I'll draw that up and show you, refresh your memory as to what these cyclical graphs look like. All right, so here's that C10, right? A cyclical graph, a cycle, a 10 cycle. And the minimal degree, that delta of C10, the minimal degree here is this is 2 regular, right? Every single vertex has a degree of 2. So that minimal degree, that delta of C10 is 2. That means that the vertex connectivity, right, kappa of C10, is going to be less than or equal to 2. So it's either 2 or 1. You're not going to see any graphs with like, connectivity of 0 because you can't remove -1 vertices or remove -1 edges. That doesn't make any sense unless you think about it as adding a vertex or an edge, but I'm not going to get into all that. All right, and then same thing goes for the edge connectivity, right? The lambda. That's also going to be less than or equal to this minimal degree of any of the vertices. So that's going to be less than or equal to 2 as well. So it's either going to be 2 or 1. All right, so I don't need to start at 10 or anything. All right, so let's talk about the vertices. All right, vertex connectivity first. All right, so I'll start off with this question. Is C10 here 2 vertex connected? All right, remember what this means. I can remove, if it's 2 vertex connected, that means I can remove any vertex and it'll still be one piece. It'll still be connected, not broken up into disconnected pieces. Well, the answer to this is yes. Watch this. Say I remove vertex 6. Then you have this 5 to 7. They're all connected. You can draw a path. Take any 2 of these. You can find an easy path to either one of them. And do this for any vertex. Remove vertex 5. Little C shape there. Remove vertex 4, vertex 3, vertex 2. No matter what single vertex you remove, the graph is still connected. So yes, right? The graph is 2 vertex connected because I can remove any 1 vertex and the graph is still connected. So this kappa of C10, the vertex connectivity of C10 is 2. All right. And to put it another way, remember the other way they put this, right? The vertex connectivity. When I say the vertex connectivity is 2, that means I can remove any single vertex and it's still connected. But there are if I want to remove 2 vertices, I can do it in a way that disconnects the graph, right? Like if I remove vertex 6 and vertex 2. Now you see the 2 pieces, from 1 to 7 and then from 3 to 5. It's broken over 2 pieces. Okay, so the vertex connectivity is 2. Now I want to get into the edge connectivity. So same start. The edge connectivity is going to be less than or equal to 2, right? That minimal degree. So I'll start with 2, right? Is C10 here 2 edge connected? All right. So again, if it's 2 edge connected, that means I can remove any 1 edge, and it'll still be connected. Still be a single piece, not broken up into multiple pieces. Well, It's pretty obvious, I hope, that the answer is yes. Say for example, I remove this edge. Remove the edge from 5 to 6. Well, look, you got from 5 all the way around. You can get from one vertex to any other vertex still. It's still connected, one big piece. And do that for any single edge, right? Any edge I remove, it's still a connected graph. So the answer is yes. So this lambda of C10, right, the edge connectivity is 2. And to think about it the other way that they had, when I say the edge connectivity is 2, that means I can remove any single edge and it's still connected. But when I start removing 2 edges, I can do it in a way that disconnects the graph. Like if I got rid of the edge from 6 to 7 and got rid of the edge from 3 to 4. See, now I have 2 separate pieces. That part of the loop from 3 to 7 on top, and then the part of the loop from 4 to 6 on the bottom. It is disconnected now. Okay, wonderful. So both, now again, not always going to happen where the vertex connectivity and the edge connectivity are the same, but they're both 2 in this case. All right, so hopefully now those definitions of vertex connectivity and edge connectivity, those can be tricky the first time you see them and come across them, but I hope I went over enough examples here to where the definition made sense, and maybe watching that animation and of course practicing exercises and looking at the solutions when you're done and seeing how you're doing. Hopefully all that stuff helps you out in understanding this. All right, so then you have your additional exercises. Again, not too many. Some are assigned, some are not. Even if I didn't assign something, I would still recommend that you go over it, right? Just to get more exposure, more practice. And of course, you have the solutions to look at if you need to. But again, like I've been saying almost every video, right? Please don't look at the solutions first. Try to work on these first on your own, figure them out. And then if you get stuck, or you did it and you feel you're confident about it, you want to see that see how you did compared to what they did, then look at the solution. Yeah, and I'm hoping this video again is a nice guide through this section. If you have any questions at all, right, send me a message and I'll get back to you as soon as possible. And thank you very much for watching.